The other trend is that people drift in like a minute or two late. So maybe I'll just wait like 1 minute before I fire up here.
Hello, Tudor.
Hey.
Hey, how are you doing?
Really nice to see you.
Yeah, nice to see
visiting
you.
Berkeley.
It's been a while. You're in Berkeley?
Yeah, I'm visiting Berkeley and then at Strata.
Oh, wow.
All right, so maybe, are you ready?
Yep.
All right, so let's see, turn on the record. So welcome everyone once again to the WHCGP. Today we are delighted to have Dalimil Mazac, who will tell us about automorphic spectra and the conformal bootstrap. If you have questions during the talk, please just go ahead and speak out. Take it away, Dalimil.
Okay, thanks very much, Andy, for the introduction, and to you and the rest of the organizers for inviting me to speak in this wonderful series. What I'll be telling you about today will be mostly work based on work with these two fantastic collaborators, Petr, Kravchuk, and Sridip, in a paper that appeared approximately a year ago. There was also a simultaneous paper by James Bonifacio, which was closely related to our paper with Petr and Sridip. And finally, I'm also going to report on some ongoing work with all of these people. So eventually, the talk is going to be about spectral hyperbolic manifolds, but I'd like to start with some more physics-oriented motivation, namely the question, what is quantum field theory? And this is, of course, a very broad question about which all of us have various opinions. And it's kind of natural to split this question into two parts. The first one is how do we rigorously define quantum field theory? And the second one is how do we compute observables? And usually, well, an approach which is good at addressing question one is not so good at computing observables, and vice versa. We have many non-rigorous ways of computing observables which are not so good at addressing the first point. But the approach to quantum field theory that I like to highlight today during the talk is the conformal bootstrap. So this is an approach which applies to conformal field theories and which to a large extent addresses both 1 and 2. So conformal bootstrap is some precise axiomatic formulation of conformal field theory in any number of dimensions. So it's not just in 2 dimensions, but in general number of dimensions. It works pretty well. And it is also good at addressing 2. So it's effective for computations and sometimes even leading to new predictions, as I'm going to review in a second. So yeah, that's conformal bootstrap. And what are these axioms? What is this sort of rigorous formulation of CFTs? Well, it essentially comes in three parts. The basic player in the game is some vector space V. So Hilbert Space, a unitary representation of the Lorentzian conformal group in d dimensions. The interpretation of it is this is the space of states, or equivalently space of local operators. And since it's a representation of the conformal group, it's natural to decompose it into irreducible representations of this group. So you can write it as a direct sum of these irreps, which are labeled by scaling dimension and a spin. The details don't really matter. They're just some lowest weight representations of the conformal group. And then there are some distinguished elements of these irreducible representations called local operators. So you can basically get, by acting with these local operators, when X ranges over the unit ball, you get a dense subspace over this irreducible subspace. Okay, but this is not it. This is not the whole story. There's an additional important structure, which is sort of a multiplicative structure on this Hilbert space, which is known as the operator product expansion, or the OPE. So this means that we can take 2 of these local operators, multiply them together, and as long as X and Y are not equal to each other, we can this defines some normalizable vector in the Hilbert space, and we can expand it using this direct sum decomposition. And this defines some structure constant,Cijk. Okay, so far we have the CFT is specified by the set of data consisting of these deltas and rows and theCijk's. And this data is constrained by associativity. So associativity is just a statement that when we multiply three operators as such, we can put brackets either like that or like that, and the result must be equal to each other. And associativity, together with unitarity, implies some stringent constraints on the spectrum and structure constants. So this is the basic idea of the conformal bootstrap. The long-term goal is to try to solve and classify conformal field theories in general number of dimensions, starting from these axioms. And this was nicely captured in a quote by Polyakov, who said that I was dreaming in the 70s to have a classification of fixed points based on the hyperbolic expansion, and the program was successful in 2 dimensions. And I think it is not excluded that in 3 dimensions, something like that is still possible. So that's a very, very ambitious goal. And at the moment, we are very far from it being realized. In fact, the current status is that in 2 dimensions, there has been some partial progress, namely on rational theories and label theory, and maybe several other examples. But really, this is even in 2 dimensions. These examples are supposed to only scratch the surface of the space of possible conformal field theory. So somehow we don't really know, we don't really understand the generic conformal field theory even in 2 dimensions. And above 2 dimensions, it's even worse. So there, the only solved examples are free theories, but surely infinitely many interacting examples exist. We just don't know how to solve them. So examples are, for example, 3D Ising model, the 4-dimensional equals for super young males, or the 0,2 SCFTs in 6 dimensions. Okay, but here's where what does the bootstrap imply? Why should we be maybe partially optimistic? Is that these axioms seem capable of isolating interacting CFTs even in above 2 dimensions. So it has been observed that one gets nearly sharp bounds on the spectral data from linear and semi-definite programming after implementing the CFT axiom. So here's a plot which is supposed to demonstrate that in 3D CFTs, where everything which is not blue is excluded. So the horizontal and vertical axis are some scaling dimensions in a 3D CFT, and the 3D Ising model is essentially, well, is almost uniquely pinpointed by these bounds. So a speculation which comes from this observation of big constraining power of the bootstrap is that maybe one day we can solve an interacting CFT in more than 2 dimensions, such as the 3D Ising model. Okay, how are we going to do that? A possible strategy is to try to identify some mathematical structure which produces the spectral data that satisfy the axioms. Right? We have some infinite set of equations which come from associativity, and it would be great to know how to produce set of spectral data, so the scaling dimensions and CIJKs, which solve these equations automatically. This was, for example, done for rational 2D CFTs by Moore and Seiberg, who showed that essentially the structure of modulo tensor category leads to such spectral data which solves the bootstrap. There was also an interesting paper by Abhijit Gada in general dimensions. But anyway, the point of the talk today is that there is a good toy model for such a structure in the form of hyperbolic manifolds. So hyperbolic manifolds give rise to some spectral data, as I'll explain, and the spectral data satisfies something like the conformal bootstrap equations. So just a quick review of hyperbolic manifolds. What is a hyperbolic manifold? Well, it's a Riemannian manifold of constant sectional curvature -1. The simplest example is the hyperbolic d-dimensional space, which you can realize as a hyperboloid in d+1 dimensions with this Lorentzian metric. And the group of orientation preserving isometries of this hyperbolic d space is the connected component of identity in SO1, D. So SO1, D just acts linearly on this space of x0 up to xd, and it acts by isometries. Here's a picture of Escher's picture of the d = 2 case. And an important fact, which will be crucial in the rest of the talk, is that you can realize any close connected orientable hyperbolic d-manifold as a quotient of the hyperbolic d space. Okay, so picking a hyperbolic d-manifold is the same thing as picking a discrete subgroup of SO1, D, discrete subgroup gamma. Okay, and then this quotient HD mod gamma is the manifold. So gamma is just the fundamental. So gamma is the fundamental group of our manifold, and HD is the universal cover of our manifold. And then the analogy, which I'd like to sort of explain, is that there is some because of this group structure, there's an analogy between conformal field theories in d-1 dimensions and hyperbolic d-manifolds. And as I already suggested, the underlying reason for this analogy is that the same group, the representation theory of the same group underlies both sides. On one hand, this SO1, D is the group of conformal transformations in d-1 dimensions, in Euclidean are d-1, which is why it's relevant for CFTs in d-1 dimensions. And on the other hand, it's the isometric group of hyperbolic d space. So this is like a very, very simple reason. And I'll put some flesh on this analogy. So here's the analogy or the dictionary, if you wish. And I just like to go through the dictionary so that you know where this is heading. And I'll spend the rest of the talk explaining the dictionary in more detail and also cover some applications of this analogy. So yeah, G is going to be SO1, D, so the group of isometries of hyperbolic d space. And under this analogy, a conformal field theory is supposed to be analogous to a hyperbolic manifold, which is a quotient like this. Then the most important player in the game is the Hilbert space. So CFT comes with a Hilbert space on the sphere, and this is analogous to the function space, to a space of functions on this coset space. So I want to insist on using functions not just on the manifold but on this G mod gamma coset space, which is sort of some kind of a bundle over the manifold. And the nice thing about this space is that it's a unitary representation of G. I can act by right multiplication on G mod gamma. And local operators are some distinguished elements of this Hilbert space. So sometimes they're called automorphic functions. So they're basically like k-finite vectors in irreducible representations in the decomposition of L2 G mod gamma. Now we can also consider correlation functions, which just come from taking a bunch of these automorphic functions or automorphic forms, multiplying them together, and integrating the result over the coset space G mod gamma. So this defines a correlator of these local operators or automorphic functions. The conformal Casimir eigenvalue is, well, for a large class of representations, it's equal to the Laplacian eigenvalue, which is related to the scaling dimension as such. And crucially, there is a natural notion of an operator expansion. The operator expansion is just a pointwise multiplication of these functions. So we can take two functions on this coset space and expand them using the sort of direct sum decomposition into irreducibles, and this defines some structure constant Cij case. Structure constants can also be realized as these correlation functions of three automorphic forms. So they're just sort of integrals of triple products of these automorphic forms. Right. So there is a large part is played by representation theory of SO1, D, but there's also some kind of dynamics. Right. Each hyperbolic manifold is going to give rise to some discrete set of deltas and Cij case, and these are going to satisfy some bootstrap equations, as I'll explain. So maybe now is a good time to stop for some questions. But as I say, I mean, this was just supposed to be schematic, and the rest of the talk will be about explaining all of this in more detail.
May I ask a question, please?
Yeah.
Thank you. So it's just the equivalence between Laplace eigenvalues and conformal Casimir eigenvalue. Is this also up to multiplicity of the Laplace eigenvalues?
Yeah. So well, okay. I'm not sure. I'm not sure if I understand the question. Well, the point is going to be that there's going to be some Hilbert space, and I will decompose it into irreducible representations of SO1, D, and then there's a one-to-one correspondence between Laplace eigenfunctions and irreducible representations of a certain isomorphism type. And this includes multiplicity. So if there's multiple eigenvalues, then there are going to be multiple copies of the same infinite dimensional irreducible representations in your Hilbert space.
Okay. So if there's a multiplicity of the eigenvalues, then there's also eigenspace is bigger. It's not just one dimensional. So that will show up on the other side.
Yeah.
Okay. Thank you.
Okay. So the goal today will be to adapt some well-developed techniques that we have been using in the Conformal Bootstrap. So we have been using on the left-hand side of this dictionary and apply them on the right-hand side of the dictionary. So we'll use them to prove some new results about the spectrum of hyperbolic manifolds. And I want to emphasize that we are going to prove them. So everything is completely rigorous, and just that even though we are inspired by physics, the kind of bounds that we learn about, there will be rigorous by pure math standards. And hopefully I'll convince you of that. I should also mention some previous work, which was very inspirational for us. So first, Bonifacio, Hinter, Bichler came up with a similar method for general Einstein manifolds. So in this case, there are just sort of finitely many bootstrap equations, but they are still quite constraining. Then Bonifacio studied hyperbolic manifolds using these ideas. But he didn't sort of emphasize the role of representation theory. So in our paper, we pointed out the role played by SO1, D for hyperbolic manifolds and phrased everything in terms of representation theory SO1, D, which I think is the right way to understand these things. So, and in particular, this also clarifies the connection to the conformal bootstrap. Okay, so having said that, I'm going to now specialize to d = 2, so 2D hyperbolic manifolds, until almost the end of the talk. But towards the end of the talk, I'll say something about 3 manifolds as well, which is something that we are working on right now. Okay, so here, just a quick overview of 2D hyperbolic manifolds or orbifolds. So here we start with the upper half plane with hyperbolic metric, dx squared plus dy squared y squared, and G, which is SO1, 2, is also known as PSO2R. It acts on the upper half plane by Möbius transformations. So ABCD is in PSO2R, and it acts as such. And these are isometries of the upper half plane. And now to get a hyperbolic manifold or orbifold, you need to choose gamma, which is a discrete subgroup of PSO2R, and take a quotient of H by gamma. We are going to assume that gamma is a lattice. So this is just a different name for saying that H mod gamma has a finite volume. And then there are 2 further cases to keep in mind. If gamma only has hyperbolic elements, so meaning that every element of gamma has a trace greater than 2, then this quotient is a compact surface without any orbifold points. But more generally, we can also allow gamma to have elliptic elements. So these are some elements that have a fixed point inside the upper half plane, and this fixed point is going to lead to orbifold points of the quotient. So what I'm going to say is going to apply to this more general second case with both hyperbolic and elliptic elements, and in particular also to the first case where we only have hyperbolic elements. Okay, and we'll be asking questions about Laplacian spectrum. So how do we define Laplacian spectrum? So Laplacian on the upper half plane looks like this, and we'd like to study this eigenvalue problem, where we want to, so the Laplace equation, lambda being the eigenvalue, h being the eigenfunction, but we want to solve it in the space of functions which live on this manifold or on the orbifold, meaning that there are functions in the upper half plane which are invariant under gamma. Okay. And if the manifold is compact, then the spectrum is discrete. The manifold has finite volume, which it will always. It starts with 0, which corresponds to a constant function, and then there is some non-zero gap to lambda 1, and then there is some discrete spectrum going off to infinity. Now, in general, there is no closed expression for these lambda i's. Well, in fact, such expressions are extremely rare. Only for some very special number theoretic cases, there are some special eigenvalues which are known exactly. And this is like kind of a reflection of the chaoticity of the classical problem. The classical problem is like a motion of a free particle on the hyperbolic surface, and this is a classical chaotic problem, so you wouldn't expect it to be able to solve the quantum problem. So this is like the Schrödinger equation for the free particle, so you wouldn't expect to solve the quantum problem exactly. And in fact, this has been a rather useful toy model for studying quantum chaos. And what I will talk about today are some new upper bounds on this spectral gap. on the lambda one. Okay, before telling you what our results are, let me just describe some examples of hyperbolic surfaces and orbifolds. The first example are triangles, hyperbolic triangle groups. And to get them, you choose 3 geodesics in the upper half plane, which meet at angles that are, so these alphas, the interior angles are pi over positive integers. And gamma in this case is generated by rotations around vertices, these 3 vertices, by angles 2 pi over ki. So just to remind you, gamma is always a subgroup of the orientation preserving part. So we don't include reflections, but we include rotations which preserve this picture. So the fundamental domain of gamma consists of 2 adjacent triangles. Here's a picture of the quotient. So there's like sort of a triangle in the front, triangle in the back, and they are glued along the edges. So topologically, you get an orbifold of genus 0 with 3 orbifold points of orders k1, k2, and k3, meaning that the angle at the points is 2 pi over ki. And the hyperbolic orbifold of minimal area is an example of these triangles. It's with k1, k2, k3 being 2, 3, and 7. And this orbifold 2, 3, 7 will play an important role very soon. Okay, so that's an example of a genuine orbifold. To get an example of a smooth surface, which is hyperbolic, you need to go to at least genus 2. At genus 2, there is a 6-dimensional moduli space. And a particular point in the 6-dimensional moduli space is a Bose surface. It's the most symmetric point in the moduli space. So genus 2 surface with a larger group of isometries. The group of isometries is the finite group, some finite group of order 4 to 8, GL2 over F3. And you can tile, so let me just, yeah. You can tile this Bose surface with triangles of the type 2, 3, and 8. So here's a picture of the fundamental domain for the Bose surface in the hyperbolic disk, and the white and gray triangles are the 2, 3, 8 triangles. And I guess there are 96 of them. In general, it's useful to talk about the topological type of an orbifold, which consists of the genus and the orders of orbifold points. So G and K1 up to KR. And this is the same. So giving this set of integers is the same thing as giving gamma up to isomorphism. But this doesn't really specify the surface completely, because there are moduli, and the moduli correspond to different embeddings of a particular isomorphism type of gamma into PSO2R. So the only topological types which don't have continuous moduli are the 3 punctured spheres, so G equals 0 and K1, K2, K3, but everything else has continuous moduli. Okay, finally, here is a summary of the results, and then I'll tell you how we actually got the results right after that. So we were able to prove that the first point is not really surprising, but it's still interesting to prove it, is that the 2, 3, 7 triangle orbifold maximizes the spectral gap among all hyperbolic orbifolds. In particular, the spectral gap is approximately 44.88835. And then we can also, among other things, we also proved upper bounds on the spectral gap at fixed genus. This is something that will be quite hard to do brute force way, because already at genus 2 there is 6-dimensional moduli space. So if you wanted to understand the spectral gap, you would sort of have to compute numerically the spectral gap, or for each point in this moduli space, and that will be computationally very expensive. And this bootstrap method that I'll describe implies an upper bound on spectral gap for any genus 2 surface or orbifold of the form 3.8388977. Okay, so that, I mean, if you want, this looks like some random transcendental number, but the rigorous bound that we proved is obtained if you interpret it as a rational number, and then any. What I mean to say is that the rigorous statement that we proved is when you interpret it as a rational number. And remarkably, there is a surface, this Bosa surface, which comes very close to saturating this bound. It agrees with the bound to about 4 decimal places. And our method beats the previous bound, which is this Yang-Yao bound, which was 4. But I should say that the Yang-Yao bound actually applies to all genus 2 surfaces, not just hyperbolic ones. So it's not surprising that we should be able to do better. Similarly, we also get a bound at genus 3, which is so every hyperbolic orbifold genus 3 satisfies lambda 1 less than or equal to 2.678. And again, this comes very close to an actual non-surface, but this bound seems to be nearly sharp. There's a fine quartic with this lambda 1, and again, our bound is a little bit better than a previous best known bound by like 0.1. Okay, so this bootstrap method that I'll describe seems to do pretty well. It basically leads to sharp or almost sharp bounds on the spectral gap. Another type of result, which is closely related, that we got is that sort of a spectrum of the spectrum of lambda 1. So the question is, what values does the spectral gap take when X ranges over all hyperbolic orbifolds? And to our surprise, nobody seems to have asked this question in literature. And by computing various upper bounds, we came up with this following picture. That there are several discrete points. There's a discrete point coming from the 2, 3, 7 triangle, which we already know is the maximizer of lambda 1, and there are 2 more discrete points corresponding to 3 punctured spheres, 2, 4, 5, and 2, 3, 8, and 3, 3, 4. So there are 2 different 3 punctured spheres with the same lambda 1 over here. And finally, there is a continuum which starts at about 15.79 and then goes all the way to 0. And this corresponds to a 4 punctured sphere. So the 4 punctured sphere has a 2-dimensional moduli space. And at a symmetric point of the moduli space, lambda 1 is maximized. And then if you take the 2 punctures, sorry, but it's not. I'm getting it okay. Sorry about it. So there's a moduli space, and when you take the pairs of 2 punctures far away, lambda 1 goes all the way down to 0. So that's why. Okay. That's why I get this continuum. And to motivate it, one can state the famous conjecture of Zellberg. I mean, to sort of motivate asking this question, which basically is a conjecture about what would be this picture if we only look at congruent subgroups of SL2Z. So in that case, the conjecture is that lambda 1 is always a quarter. So this picture, if you restrict X to be a congruence orbifold, would be a single isolated point at 1/4. Okay, so that's the statement of results. Okay, there seems to be a question in the chat. Is this a spectrum of some interesting operator? Yeah, that's an interesting question. So like an operator. Yeah, I'm not sure what the operator will be the space that this operator acts on. I mean, it's of course not how we obtain it. It's just I'm not that I know of. Okay, so that's the results, and now in the rest of the talk I'll describe the method. And the method follows the blueprint of the conformal bootstrap. So first we need some Hilbert space and local operators. Then we'll need some operator product expansion. And by imposing associativity, we get bounds from linear programming. Okay. Are there maybe any questions so far?
Maybe I can just, does your method extend to 2-dimensional manifolds with cusps as well? So does it include SL2Z?
It includes SL2Z, but the results are not particularly interesting at the moment for SL2Z. So the SL2Z has a continuous spectrum starting at 1/4.
Would have, yes, because of,
so SL2Z is the cusp. So there's a continuous spectrum starting at 1/4. So the spectral gap is the spectral gap that we would. Well, 1/4 satisfies all of our bounds, sort of trivially. All of our upper bounds are way above 1/4. So SL2Z, I mean, it agrees with it, but it doesn't saturate anything.
I see. Okay, thank you.
I mean, it would be great if one could somehow do SL2Z, but be able to distinguish the continuous part of the spectrum and the mass cusp forms. But we don't know how to do that. So from our point of view, basically the mass cusp forms and the Eisenstein series are on an equal footing.
All right, thank you.
We cannot pick them apart. Yeah, but it's a great question. Okay, the Hilbert space is this sort of automorphic space L2 G mod gamma. A G mod gamma is a 3-manifold, which is a circle bundle over the surface. So X here is the surface. You know, you get the surface by quotienting on the right by K, which is the maximal compact subgroup of SL2R. And when we consider the space of L2 functions on this 3-dimensional space, it's a representation of G because we can act by red multiplication on these functions. And it's a unitary representation because the inner product can be taken like that, and it's this is a Haar measure, so it's G invariant. You get a unitary representation. Now, what is this? What is this Hilbert space? Well, one way to understand it is to decompose it under the action of the maximal compact group, which is just the circle. So it's like a Kaluza-Klein decomposition around this circle, labeled by the momentum around the circle, so it's a representation of SO2. The functions in V0, so they are invariant under rotations. They are just functions on the surface itself. So these are just sort of scalar functions on the surface, and the Vn consists of L2 normalizable n forms. So they are objects on the upper half plane, such that this fxy dz to the n is invariant under gamma. Okay, so they're like modular forms or forms of weight 2n.
Sorry, I missed. Where did the circle come from?
The circle is a part of this G, right? So G contains a circle, which is
G was a group.
Yeah, G is a PSL2R in the rest of the talk. Okay, so and this contains SO2R or PSO2R as a maximal compact subgroup. Okay, so if you quotient G mod K, so let me call this K, you get the upper half plane. Okay, if you quotient on the left by gamma, you get the surface. So this thing is X, is the surface. But now I want to not quotient on the right by K. So I'm putting the circle back.
And we should no longer think of SO plus 1,3.
It's SO 1,2. PSO, yeah. PSO, it's a two manifold. I'm focusing on the d equal 2 case now.
Thank you.
Okay, good. Okay, so yeah, the big picture is here. The X is the hyperbolic surface, and then there's this extra circle now. Putting in the circle is
just to clarify, geometry. This circle bundle is just the unit is the circle bundle in the tangent bundle of the surface.
Yes.
I mean that's what. Yeah.
Mm-hmm. I mean the reason I'm putting the circle back in is to get a representation of PSL2R, because now the generators of PSL2R, they can move you between the different momenta on the circle. Like the raising and lowering operators raise and lower the momentum around the circle. Okay, so now that I have that, let's take this Hilbert space and decompose it into irreducible representations of the group that acts, which is PSO2R. And here's the decomposition. There is a trivial representation appearing only once because the action is transitive. So, and these are the constant functions. And then there is a sum over principal and complementary series. These are some infinite dimensional representations of PSL2R labeled by lambda, which is the Casimir eigenvalue. And then there is some discrete series. But these principal series, they come from Laplace eigenfunctions with eigenvalue lambda. So there's a one-to-one correspondence between Laplace eigenfunctions on the surface and and principal series or complementary series representations in this decomposition. And the discrete series states So these are some lowest weight and highest weight representations. They correspond to holomorphic modular forms of weight 2n. Okay, so the discrete series comes with a label n, and a holomorphic modular form of weight 2n give rise to such a discrete series representation. I mean, I could say a bit more about it if people are not familiar with it. So each of these p's is some infinite dimensional representation, but it contains precisely one-dimensional subspace, which is SO2 invariant. So it contains precisely one function on the surface. And this is the Laplace eigenfunction. And similarly, this dn is a lowest weight representation. So it contains a one-dimensional subspace, which is the lowest weight subspace. And this one is precisely the holomorphic modular form. So it's something in the lowest weight condition means it's annihilated by the anti-holomorphic derivative, which is why it gives rise to a holomorphic form. Is this okay? Shall I? I mean, when I was, at some point I learned something about modular forms, and I knew about irreducible representation of PSO2R, and only sort of during thinking about this project I realized that they are the same thing. So somehow this is not always appreciated by physicists. That the lowest weight representation of PSO2R in this L2G mod gamma is the same thing as holomorphic modular form. But it's a true fact. So yeah, the task of spectral decomposing this Hilbert space into irreducibles is the same as the task as solving the Laplace equation and finding the spectrum of modular forms. And the question that one would like to ask is, what are the constraints on the set of representations that appear here on the right-hand side? And there are two ingredients that we are going to use. The first one is the Riemann-Roch theorem, which basically fixes the spectrum of the discrete series in terms of the topology. So the topology consists of the genus and the orbifold degrees, and there is just a closed formula for how many times this discrete series representation appears for a given topology. So the degeneracy does not depend on the moduli, but the spectrum of the Laplacian depends on the moduli, and we're going to constrain it using associativity. So there's a product which is pointwise multiplication on G mod gamma, which is gene variant, and associated with this product, together gene variants will lead to bounds on, say, lambda 1 in this part of the spectrum, given some simple information about discrete series spectrum. All right. So now to make the analogy with CFTs a bit more precise, let me define local operators in this setting. So local operator starts from some functions in G mod gamma, which is a lowest weight vector in a discrete series representation. In other words, it's a holomorphic modular form of some weight n. And then we can define O of W, which in physics we would call a local operator, as some other vector in the same irreducible representation. So it's a vector which we get by acting with this group element on the lowest weight vector. Here is just, it's kind of like a generating function for all the descendants. And when W, which is this auxiliary variable, this W has nothing to do with position on the surface, it's just some auxiliary variable which parameterizes different vectors in the infinite dimensional era. So when this W is inside a unit disk, O of W is a vector in this lowest weight representation. And under the action of SO2R, it behaves exactly like a conformal primary operator of scaling dimension n. But we don't have the full grossor. We only have the L0, L plus or minus 1 in this case. And similarly, you can define a conjugate operator O bar using a sort of similar logic from the complex conjugate of the modular form. Okay, having defined local operators, you can define correlation functions. So just start with a bunch of automorphic forms in this space. Taking a product, and the correlator is defined as the integral of the product, appropriately normalized so that expectation value of 1 is 1. And because this measure is just the Haar measure, the correlation functions are invariant under SO2R, which implies some nice properties. So for example, 1-point functions vanish unless you're taking a 1-point function of the identity. And 2-point functions look exactly like in a CFT. of a two-point function of two conformal primary operators as a function of W1 and W2. And so do three-point functions. So for example, three-point function between OO and O bar depends on the W's as such. And it comes with an overall constant, which is some CIJK. Which is also a structure constant in the OP. Okay, so I already said the word OP, but what exactly do I mean by it? The upper expansion is the idea that you can take a product of two of these local operators and use a spectral decomposition in L2 G mod gamma. Okay, so each O for some fixed W1 is a function on G mod gamma, as is O bar W2. So this product, I'm suppressing the dependence on G. I mean, this product is also a function on G mod gamma. So I can decompose, I can use a spectral decomposition of this space to express it. And for O bar, I get a contribution of identity of the triple representation and a contribution of the Laplace eigenfunctions. And for O and O, so this is some lowest weight, it's a product of two lowest weight representations, I get a contribution from the discrete series. Okay, so these C's, Ci and Cj, there are some dynamical numbers which depend on the specific manifold, as is the spectrum of lambda i's, but the spectrum of these Nj is much more rigid. It only depends on the topology of the manifold. And these K's, they are universal in the sense that they only depend. Their dependence on W1 and W2 is fixed by gene variance. So there's the reason is that there's just a one-dimensional space. This is like the uniqueness of three-point functions in a CFT. Okay. And these dynamical numbers, Ci and Cj, they are some integrals of triple products of automorphic forms. Okay, so that's the OPE. And now the thing that we need to do is to impose associativity, which we can do most efficiently by considering the four-point function. So let's suppose that we have a holomorphic form of weight 2n. So there's some discrete series representation inside here, and On is the corresponding local operator. So then we consider the four-point function like that and expand it in two different channels using the OPE. So we get two different infinite sum representations of the same quantity. In practice, you can absorb all of the dependence on Wi's into a single cross ratio. So you get an equation parameterized by a cross ratio chi, which looks like this. On one hand, you're summing over the Laplace eigenvalues of a conformal block. That's usually a 2f1 function, depending on the cross ratio and depending on the Laplace eigenvalues. And on the other side, you're summing over slightly different type of 2f1, so a different conformal block, which depends on discrete series spectrum. But the bottom line is that we get some infinite number of spectral identities, which we can get, for example, by expanding this equation around chi equals 0. So we get an infinite number of identities satisfied by the spectrum, which is sort of the only thing that we'll need in the rest of the talk. So just to summarize, we have assumed that H mod gamma has some holomorphic modular form of weight 2n. And then let's take Hi to be the complete set of Laplace eigenfunctions, and let's define the Ci to be the overlap between the norm squared of the holomorphic modular form into this Hi eigenfunction. Then this data, the spectral data I've explained, satisfies some infinite number of spectral identities, which take the following form. So we are summing over all of the Laplace eigenvalues I of Ci squared times some polynomial, and this is either equal to something positive, some dm squared for even m, or to 0 for odd m. And these polynomials are completely explicit, so they come from expanding these two f1s around chi equals 0. So these polynomials, they just come from representation theory of PSL2R. They don't depend on the surface. The only thing that depends on the surface is the spectrum of lambda, Ci's, and the dm's. And the reason we'll be able to use this to prove some bounds is that both the dm squared and Ci squared are positive, because dm and Ci are real. So for people who are familiar with the Conformal Bootstrap, this is quite a familiar setup. And the way to leverage it to prove some interesting bounds is to use linear or semi-definite programming. So here is how it goes. So we have these spectral identities, which I explained on the previous slide. And the following proposition explains how to get a bound on lambda1 from these identities. So first, we truncate these identities to some, we only use finitely many of them. So capital M tells us how many of these identities we are using. And eventually, we want to take M to infinity to get the optimal bound. And let's consider some linear combination of these polynomials with coefficients xm. And let's impose some constraints on these coefficients. So first, we want them to be non-positive for even m. Then we want to normalize it such that q of 0 is 1. And finally, we want it to be non-negative above some lambda star. Okay, so the claim is that if you have constructed such a linear combination of these non-polynomials, then you have proven an upper bound on the spectral gap, lambda1 being less than lambda star, for every hyperbolic orbifold with a holomorphic form of weight 2n. So why is it? It's if there's a holomorphic form of weight 2n, then these spectral identities are valid. Then you consider this linear combination. Since all of the even x's, well, okay, then you consider this sum of ci squared times q of lambda I, and because all of the even x's are non-positive, you conclude from these identities that this sum must be non-positive. But that means that there has to be at least one lambda I in the negative region of Q. And the negative region of Q is bounded between 0 and lambda star. So there has to be at least one Laplace eigenvalue less than lambda star. In other words, we get an upper bound on lambda 1. And the strategy then is to minimize lambda star by optimizing over these axes, which satisfy 1, 2, 3, and increase the number of identities that we are using to improve the bound. In practice, we use this semi-definite programming solver SDPB, which is standard tool in the Conformal Bootstrap. Okay. And finally, here are the results. So a nice useful fact is that for every hyperbolic orbifold, you can convince yourself that there is always a modular form whose n is either 1, 2, 3, 4, or 6. So we can just run the linear program for each of these values to get some bound. And here are the results. For example, for n equals 1, our bound is about 8.47. And you can compare this with the largest lambda 1 that can be found for an orbifold which contains a modular form of weight 2, or n equals 1. And this seems to be the torus with 1z2 puncture at a special point in the moduli space. And the largest non-lambda 1 is pretty close to the upper bound. And something like that happens for pretty much all of the other values of n, maybe with the exception of 4. Maybe most sharp bound is for n equals 6, where the method from the previous slide gives 44.888 something, and that's very close to what can be numerically computed for this 237 triangle. Okay, and in particular, you see that all of these upper bounds are less than the one for n equals 6, and each of these upper bounds applies because every orbifold has one of the values of n. Every orbifold satisfies lambda 1 less than one of these numbers. So in particular, every hyperbolic orbifold satisfies that lambda 1 is upper bounded by this 44.8883537, which happens to be very close to the 237 value. Okay, then there's a question of sharpness of the bounds. So is this linear programming upper bound on lambda 1 sharp as we increase the truncation to infinity? If yes, the linear program must reconstruct the full Laplace spectrum of the 237 orbifold. And that may be happening. We are not quite sure, but there's some evidence that it may be happening. So if the bound is sharp, then this auxiliary function, q of lambda, has to vanish on the entire spectrum, because that's the only way that this equality can be sharp. So we can compare this expectation with the actual output of the linear program for m equals 41. And you get that the output of the program is this curve. So it's a polynomial of degree 41 in lambda, and the polynomial has a simple zero at 44 point something and a sequence of double zeros at higher values of lambda. And these double zeros are indeed very close to the actual eigenvalues, the higher eigenfunctions of the 237 orbifold. So it's quite nice. I mean, the only input to this, the only input to get this picture is that there exists a modulo form of weight 12 or n equals 6. And then by maximizing lambda 1 or by running this linear program for n equals 6, you get this picture. So you basically get the entire spectrum of the 237 triangle for free. And the proof of sharpness of this bound would amount to an explicit construction of Q of lambda in this infinite truncation order, m equals infinity. Okay, are there maybe any questions about anything I said so far? Okay, so let me I just want to make some comments about these infinite dimensional linear programs. So something interesting is that a very similar linear program can be used to prove upper bounds on sphere packing density in d dimensions. This was explained by Conan Elkis in 2001. And in this case, the role of the spectral identities is played by the Poisson summation formula for lattice in R to D. And famously, Vyazovska several years ago proved that this Conan Elkis linear programming bound is sharp for d equals 8. So she proved that this linear programming bound is exactly saturated by the E8 lattice in 8 dimensions by directly constructing the optimal Q of lambda or the analog of this function Q of lambda in the case of the Poisson summation formula or from the Conan Elkis context. And then with some collaborators, she found a similar saturation in 24 dimensions, in which case the optimal packing corresponds to the Leech lattice. And quite remarkably, there was a very similar line of development in the Conformal Bootstrap literature. So there, the analog of the Conan Elkis linear program is a famous founding paper of Ratatserich, Kovtuni, and Vicky, who showed how to use linear programming to prove upper bounds on the spectral gap in a CFD. So this was the paper that basically started the recent Conformal Bootstrap in higher dimensions revolution. And then in 2016, I was asking the question whether we can prove some of these bounds in a sharp way, and I was able to do it in a 1D conformal for a case of sort of 1D bootstrap with SL2R. And I didn't know anything about sphere packing at that time, but then after I came to Stony Brook and I started working with Rastelli and Tom Hartman, we actually realized that there is a precise mapping between Vyazovska's proof of the saturation in 8 dimensions and this proof in the context of 1D CFD. So, one could imagine that maybe even if Vyazovska didn't come around, physicists could have used my method from 1D CFD to solve the sphere packing problem before mathematicians. But of course, that's not what happened. Probably, if it wasn't for work of Vyazovska, we wouldn't have actually even realized that there was such a mapping. But I think it's sort of a very, very curious that our papers appeared in the same year. Well, the challenge in the context of this talk is to figure out whether the linear programming upper bound is sharp for 2D orbifold. So to sort of come up with the analog optimizer of this magic function. So she calls it magic function, Vyazovska. And for CFD, it's called the analog extremal function. Okay, then I already mentioned some bounds at fixed genus. So how do we get upper bounds on lambda 1 for all genus G orbifolds? Well, here the basic piece of information is that at genus G, there are G linearly independent holomorphic 1 forms. So the degeneracy of the n equals 1 discrete series is G. And one can use the bootstrap equations for 4-point functions of this type, where I, J, K, and L run from 1 to G, to set up a very similar linear program or semi-definite program, which is like a matrix generalization of the original problem, and which has been studied quite intensely in the Bootstrap literature under the name mixed correlated Bootstrap in the context of the 3D Ising model, for example. So basically, most of the work has already been done by these people. We just had to adapt it to the present setting, and then we got these bounds at genus 1, genus 2, and genus 3. And I already showed you at genus 2, it's nearly saturated by the Boso surface, and genus 3 by the Klein quartic. I should just make a comment maybe about the rigor. In practice, to make everything completely rigorous, one should use rational arithmetic. This SDPB program doesn't work over rational numbers, but what you can do is that you can sort of take the Q of lambda, which is output of SDPB, you can rationalize it, and then you can check that this rational function satisfies all the constraints rigorously. So in that way, you really have a rigorous proof of all of these bounds. Next is this: how do we get this picture? So this is the picture. What are the possible values of lambda 1 when we arrange over all hyperbolic orbifolds? Now, the idea is quite simple. We already know that there is nothing above about 44.88835. So what we need to do, for example, to show that there is an isolated point here, we just need to prove an upper bound on everything which is not the 237 triangle. Okay, and to do that, we can study, say, this associativity of two holomorphic forms of minimal weights N1 and N2. And it's not, you can indeed show that the upper bound from the Bootstrap on everything which is not 237 is strictly better than the eigenvalue for 237. And then you can sort of continue in the same spirit, lower and lower, prove an upper bound on everything which is not 237 and 245, and so on, until you hit the continuum. So the part which is not rigorous at the moment is where exactly does the continuum start, because that's a harder problem. So we have an upper bound on everything in this moduli space 2223, but we are not really sure. We cannot prove rigorously at the moment that the point which maximizes lambda 1 in this moduli space is indeed this special point corresponding to the 239 triangle. But everything in the picture is pretty much rigorous. Okay, and finally, some work in progress about 3 manifolds with James and Petr and Sridip. Here's a picture from our upcoming paper where, so on the horizontal axis is the lowest spin 1 eigenvalue, hyperbolic 3 manifolds, and on the vertical axis is the spin 2 Laplace eigenvalue, where the spin refers to the rank of the bundle that we are acting on. So in 3 dimensions, you can consider Laplacian acting on vector fields, which is what I call spin 1, and a Laplacian acting on symmetric tensors of rank 2. That's the vertical axis. The red dots are the values for various compact hyperbolic 3 manifolds that we computed using the Hilbert trace formula. Sort of there's a beautiful piece of software called SnapPy or SnapPy, which is a database of hyperbolic 3 manifolds. And this database, for each hyperbolic 3 manifold in the database, it gives you some presentation of gamma. And from there, you can get lengths of closed geodesics on the hyperbolic manifold and then feed it into a trace formula to compute pretty well the lambda 1 for both spin 1 and spin 2. And you can sort of see that the red dots lie in some region, which should be upper bounded by something. And indeed, the adaptation of the same method that I explained today in 2D, if you adapt it in 3D, you get an upper bound on lambda 1 and spin 2 as a function of lambda 1 spin 1. And the upper bound from the Bootstrap looks like that, the blue curve. And it seems, there are even some points which basically saturate this bound. I mean, there are some points which seem to violate it, but that's just because we didn't compute the position of the red dot precisely enough. But the red dots are not rigorous. The blue curve is rigorous. So it seems to be working pretty well also for 3 manifolds. Finally, some future directions. I didn't talk much about the CIJ case today, but they are very interesting. they are related to values of L functions using something called Watson's formula. So in the arithmetic cases, theCijk can be computed using in terms of some values of special values of L functions, and upper bounds on these L functions is a big question in the number theory literature. For example, Lindelof hypothesis is a type of an upper bound which is something, is the kind of upper bound that maybe the bootstrap can say something about. And in fact, some recent papers in the number theory literature use a very similar method of this associativity. These papers by Breston Reznikov, Michel Venkatesh, and Paul Nelson, they use some arguments of a very similar flavor to this bootstrap to prove some best known bounds on L functions. Related to that is the question of bounding non-compact orbifolds. So there was already a question earlier in the seminar about SL2Z and maybe understanding what role arithmeticity plays. So there we have some extra symmetries coming from the Hecke operators, which sort of should enhance the SL2R to some bigger group. And finally, it would be nice to use this toy model of hyperbolic manifolds to learn something about the thing that I care about much more, which is actual CFTs. So that's all I have for today. Thanks a lot.
Great, thank you very much. So let's thank the speaker. And so now we have time for some questions. If you have a question, I think just go ahead and unmute yourself and speak out.
Hey, Dalimil. Quick one. Can you detect anything about like rigidity of certain representations in 3 dimensions or dimensions of moduli spaces in 2 dimensions?
Well,
I don't know, from counting operators of certain dimensions.
Yes and no. Well, yeah, not quite. Yeah, we don't really like. Yeah, I guess we have this picture, for example, for the spectrum of lambda 1, which, I mean, we were able to show that, for example, this is an isolated point, right, which is related to the rigidity of the fact that of the 3 punctured spheres in 2 dimension. But we weren't really able to prove that the solution of the spectral identities is rigid. It's more like that we are using the fact that we have some discrete labels that we can prove a bound on everything which is not 237. So yeah, I think to really probably to understand rigidity, to prove rigid, I guess the question is everything which is true about the spectrum a consequence of these identities? Then if yes, then eventually, so in 3 dimensions, we should be able to use these spectral identities from Bootstrap to prove that solutions are rigid. But probably to do that, we would really have to implement crossing for more than one 4-point function, maybe infinitely many 4-point functions. At the moment, we just have an upper bound on lambda 1, and anything below the upper bound is allowed. So, yeah, am I?
Yeah, no, thanks. I was wondering if there were like some operators in the spectrum that would be related to deformations.
Oh, I see. Okay. Yeah, good.
And that may be the wrong intuition.
Yeah. Well, there are. Yeah, that's right. So the deformations correspond to these holomorphic sort of differentials of weight for n equal to 2. These ones, right? They're like weight for modular forms. Their number is the same as the dimension of the moduli space. So.
And there's no way to rule out their existence.
Well, it's not. So in this work we were going sort of in the opposite direction. We were using this rigid spectrum of holomorphic guys to say something about the non-holomorphic guys, which are not so rigid. But maybe you want to. Yeah, I'm not sure what to be. I mean, we already know for a given topology, we already know what is the spectrum of the holomorphic form. So I'm not sure it would be a good question too.
Yeah, thanks for the awesome talk.
Yeah, thanks.
So thank you so much for the great talk. That was really cool. It just well, one first is a comment that there are conjectures of Sarnak, I think, again, and literally nothing is known about the multiplicity of eigenvalues on the modular curve. I mean, I just know about the modular curve case, maybe for other hyperbolic surfaces as well.
Yeah.
But over there, it's an old problem of figuring out what are the multiplicities of eigenvalues, or if there are any multiplicities at all. I mean, they're like, and so, I mean, if you have a comment about that, I'd love to hear. But my the next thing was a kind of a vague question. Can you prove Weil's law with these operator product expansions and techniques from CFT? Because the only proof that I have seen, I'm sure there are more, but the only one that I have seen is using the Selberg-Trace formula. By using the fact that they're equivalent to closed geodesics and figuring out the asymptotics of the geodesics, and from there translating back to asymptotics of the eigenvalues. So if one can get a direct proof of that, that would be very nice.
Yeah, they're great questions. I'm afraid the answer to both of them at the moment is no. About the first question for the multiplicity, it's a question about, for example, SL2Z.
Yeah.
And again, we run into the problem of not being able to distinguish the Eisenstein series from the mass-cusp forms, and the degeneracy is the one for mass-cusp form. So, yeah, I think if we could somehow take care of the Eisenstein series contribution, then we could potentially learn a lot of interesting things about a mass spectrum, but we don't know how to do that yet. And for the Weil law, well, you can sort of see in this, for example, in this picture of this extremal functional, we get for free the spectrum of some low-lying eigenvalues, but to correctly approximate the higher eigenvalues, we will have to push the truncation to higher and higher orders. Eventually, presumably, this eigenvalue should eventually, these zeros should eventually satisfy the Weil law.
Yes.
But it looks like both in the CFT literature and in this case, the Bootstrap has been better at sort of answering questions about low energy, the low-lying spectrum rather than the high-lying spectrum.
Right.
Sort of, yeah.
I see.
Yeah,
I mean, so in regards to this, there is another thing. I think this again was done by Sarnak, or at least pioneered by Sarnak. That is, if you fix a hyperbolic manifold, and suppose you have a sequence of coverings of that manifold, and you see how the λ1 increases in this covering, that the asymptotics of this growth of λ1 are related to the volume of the initial manifold that you started off with. So I don't know if that's helpful or not, but I mean, one thing is if you have a covering of manifolds, does CFT tell you how the λ1s will increase in this covering?
Well, I would have expected, if I have a coverings of higher and higher order, then λ1 should go down, because I'm making the space bigger, right? I can only add eigenvalues, so λ1 could decrease, not increase. Am I getting confused here?
Maybe I'm getting confused. I'm not sure.
Well, but yeah, there could be some statement about the asymptotics of λ1 as you take the covering being very large, and CFT has something to say about it. Well, a covering, having a covering is like having an extension of some solution of the Bootstrap. Right? The small manifold is some solution, and the statement is you can extend it to, you can add some more eigenvalues to it.
I see. Yeah.
I mean, that's all I can really.
I guess, I mean, if the covering is regular, that there are no branch points, then gamma for the covering is a normal subgroup of the original group. So it's true that it's becoming smaller and
in that case, you get a global symmetry type of thing, where the quotient of the two gammas is a global symmetry of the solution of the Bootstrap for the bigger.
Okay. So the global symmetry being the deck group acting on the covering.
Yeah.
Right. That's the quotient of the two gammas. Yeah. Okay. I see.
So you could try to implement sort of this global symmetry in the present. Implement the Bootstrap in the presence of this discrete global symmetry.
Very nice. And this was just to understand things. So may I just ask if you can say a word about the relationship with the values of L functions? I guess it was related to the zeros of the L function. It was bounding the zeros of the L functions, or what exactly was the?
Well, I think it's really the value of the L function, for example, on the critical axis, and so.
Exactly. I mean the conjecture, or I think in these L functions. So what are these? Are L functions of what exactly?
It's pretty general, but most concretely, you can think about the Rankin-Zilberg L function. So, for example, pick a holomorphic modular form, and then compute the triple. Then there's an L function, which is like a Rankin-Zilberg convolution of this modular form, its conjugate, and the Eisenstein series. So it's a triple product like that, where Hi, Hj are the modular form, its conjugate, and Hk is the Eisenstein series.
Right. Okay.
Then you can ask about theCijk as a function of k, where k is the parameter of the Eisenstein series, goes along the critical axis, and you can try to prove a bound on that.
Okay. Yeah, and I think the zeros of this function arise on the critical axis.
Well,
it's like
that's an important hypothesis.
Yeah. True. All right. Thank you so much. That was very nice. Thank you.
Thanks.
Guys, just one other thing. So your story, the way you phrased it, it was kind of about the representation theory of SO, 1 comma D. Is there anything special about SO 1 comma D? Could you imagine doing it to study automorphic forms of other groups?
Yeah, from the point of view of this talk, it's not really that special. Yeah, you could imagine doing it for other groups. Something that is going to fail in general is this uniqueness of the 3-point function. So this, basically the question is, if you take a product, if you consider these maps, so suppose you have two irreducible representations of your group, and you want to understand these types of G-invariant maps, then for SL2R, the space of such maps is always at most one-dimensional, like this uniqueness of 3-point functions. But for other groups, it can be infinite dimensional. So you may need like infinitely many types of these Cs to parameterize your problem, which may or may not slow you down. I don't know.
At the level of dreaming about it, it doesn't slow me down.
Yeah, but okay. for actually, there's a theorem which says that the only groups for which these spaces are finite dimensional are products of SO1 comma D. That's well for all representation, of course. For other groups, there may be representations for which these are still finite dimensional.
I see. All right, thank you.
Have you thought about trying to get bounds on lambda 2, for example? I mean, is that value of 144, whatever it was, close to being optimal? That would be a kind of interesting question.
Oh, this one. Yeah, that's an interesting question. Yes. We have. So one thing you can do is to well, I think the only way to do it at the moment is to use for example, the first eigenfunction as a local operator, as this external one. So I explained what happens when the external operators are in a discrete series, but you can play the same game when they're in a principal series. And then you can basically get some kind of exclusion plot in the space of lambda 1, lambda 2. You can ask what is the allowed region in this space from this method. So it'll be very similar to what people did for the 3D Ising model. Where, for the 3D Ising model, you have a exclusion in the space. Delta sigma is literally lambda 1, and delta epsilon is lambda 2, and there is some nice small region which is allowed. Something like that could happen for hyperbolic manifolds, but we haven't done it.
Okay, thanks.
All right. Well, I think we should probably wrap it up here. So let's thank the speaker again.
Thanks for the great questions.
and hope
Yeah,
to see you
thanks
again.
a lot.
Hope to see you again in 2 weeks when we'll have Natalie Paquette. All right, I'll end the recording, but I'll leave the room here in case someone wants to keep
Thank
talking.
you. May I bother you a little more, Dalimil, if it's okay?
Sure. Yeah.
I was just wondering, so for example, for genus 2, you showed that the extremal surface is the Boltzmann surface.